Okay, well, I want to get started because this lecture actually turns out to contain some really challenging material conceptually, and so I want to make sure we spend some good time on the difficult parts, and hopefully we'll make it through, and it'll all make some semblance of sense. Now, you remember the last time we started talking about normal forms? We talked about first normal form, like that was the boring one. Well, I guess that's not the boring one because the most boring one, second normal form, we don't even talk about anymore. But first normal form is everything has atomic attribute domains, so yay, good for us. Then we talked about Boyce-Codd normal form, aka BCNF. Again, you probably don't need to memorize these terms beyond 121. I mean, I'd like you to know them and use them in 121, but unless you become a real big database person in your future, you probably don't need to memorize what BCNF is and so forth. But anyway, this is a really good normal form because it identifies any unnecessary redundancy that can be identified through functional dependencies. Okay? Even that statement should make you think, because it's kind of begging a question. Well, is there redundancy that can be identified in ways other than through functional dependencies? And the answer is yes, but we haven't talked about that yet. We'll talk about that in a future lecture. But anyway, so if we have a functional dependency where alpha functionally determines beta, remember if we have a tuple, or let's say we have a schema with alpha and beta in the schema, for every tuple, or let's say every pair of tuples with the alpha parts the same, the beta parts have to be the same. That's what a functional dependency is. Okay? And so anyway, where alpha union beta is in R, at least one of these conditions must hold. So either it's a trivial dependency or alpha is a super key for R. Now, again, I'm going to keep reiterating this because it's kind of a big pet peeve of mine, and it's a pet peeve for a good reason. We call these dependencies trivial because they apply on all relation values. It doesn't matter what relation value you were able to concoct, it's not possible to violate the functional dependency. Okay? It's not that it's not meaningful, it's that it's always satisfied. Okay? Now it turns out that when we're talking about trivial functional dependencies, they also are not meaningful. So that's where the confusion oftentimes comes from with students. But it turns out that there's other kinds of dependencies that can be trivial, but also very meaningful. And so I want to make sure that I get that terminology straight in your heads from the very beginning. Okay, we talked about converting a schema into Boyce-Codd normal form. So you have a schema R, and it's not in Boyce-Codd normal form. Okay, well, what does that mean? It means that it has some non-trivial functional dependency that holds on R. So notice I say alpha functionally determines beta. Alpha and beta are both in R, because otherwise we don't care. And also, like I say here, F plus, remember that means the closure of F. That's the set of functional dependencies you can logically imply from F, whatever F is. Okay? So we replaced R with two schemas, and we wrote it this slightly weird way, alpha union beta. Okay, that's fine. Typically, if this is a minimal functional dependency, meaning that it doesn't have any extra attributes that don't add any meaning, we could in fact get rid of them. We'll talk about that very briefly today. Then alpha union beta together means that alpha can be a key. So you could actually underline the alpha attributes because now you have a primary key for that schema. And then you have R minus beta minus alpha, and we just write it that way because we haven't talked about extraneous attributes yet. In general, alpha and beta do not overlap because it's not meaningful for them to overlap. And so we can just write R minus beta. Just so you know where the road is headed. We want to, because this is a bit of a difficult way of formulating it initially. We may not be done. We may need to repeat this. And that's what you'll notice on assignment 6, unless you're one of those people who loves writing computer programs, which, you know, if you are, awesome, so am I. But you can do all this stuff with computer programs. And in assignment 6, you're perfectly allowed to write computer programs to solve the questions. So take some time. And in fact, you probably will take more time than just solving the problems directly. But it's really fun. So I didn't want to deny people the opportunity to do so. Okay, so we need to be able to reason about these functional dependencies. And The big issue that we have is you might have a set of functional dependencies. Remember, we call this capital F. But we don't just care about those. We also care about all the dependencies that can be logically inferred from that set F. And of course, if we take that and expand it to all functional dependencies we can possibly infer from F, then we call that the closure, and that's F plus. Okay? So let me see what else I have here. Yeah, so which attributes are functionally determined by a particular attribute set? Now, you may not know why these questions are useful, but I'll try to show you as we go through this. What minimal set of functional dependencies must actually be enforced in a database? Is a particular schema to composition lossless? Remember when we took that employee table and we chopped it in half, but we chopped it in half on employee name? That was a terrible idea, right? Because then when we tried to join it back together, we lost our minds, right? So that's an example of a lossy decomposition. Also, does a decomposition preserve dependencies? Okay, so we need to be able to figure out these questions. And so you see a relation schema R. Okay, so again, you have a schema capital R, and typically you'll have a set of functional dependencies capital F that you expect the database to set. So this F thing is sort of a way of stating all the constraints of your enterprise that you're modeling. It's not just random, right? It's supposed to correspond to something that you care about. So you say a functional dependency lowercase f on R is logically implied by capital F on R if every relation instance that you came up with that satisfied capital F also satisfied that lowercase f. Okay, that's fair, but that's not very exciting. So remember I had the example like A functionally determines B and B functionally determines C. Then we can infer from those two that A functionally determines C as well. So if we created tables of A, B, C and just populated it with data, and we knew that the functional dependency A functionally determines B holds and B functionally determines C holds, then you would note that always on those tables of data that A functionally determines C as well. That's all we're really saying here. Okay. So here is an example, and again, I'm going to point out something, because every time I see this, I'm slightly disturbed by it, and I hope that you'll be slightly disturbed by it too, once I point out the thing that disturbs me. So A, B, C, G, H, I. And then we have these functional dependencies. So A functionally determines B, A functionally determines C, CG determines a couple of things, H, and it determines I, B functionally determines H. And then I have listed a couple of functional dependencies that you can infer from this. Now you may look at this and say, okay, I think I see the reason why these things are logically implied by F, but we'll talk about the reasons and the rules that you can use to do that. The thing that I want to point out about this is, what are A, B, C, G, H, and I? They're just like attributes, right? I mean, they're just weird attributes that Donnie threw out onto a slide. The schema's name is capital R. What does it mean? What does it represent? We don't know, right? And so this is kind of the fundamental, to me it really illustrates the fundamental issue with functional dependency theory as an approach, because you'll notice that as we go through this, we're going to be reasoning about these attributes. We're going to say, hey, we've got A functionally determines G, and B determines I, and junk like that. But what does that really mean? And so this is getting back to, I mentioned it briefly on the last lecture. I'll mention it again. I'm fine doing that. But the idea back in the 70s, when functional dependency theory was first developed, and people were exploring this stuff, is, well, I can come up with my set of attributes, like my bank. Okay, so I have loan ID, I have amount, I have branch name, I have customer ID, I have customer name. And what I'll do is I'll come up with a big bucket of all my attributes, and I'll come up with another big bucket of all my functional dependencies. Like loan ID functionally determines amount, account ID functionally determines balance, customer ID functionally determines a whole bunch of other customer details, blah, blah, blah. And then I'll push this magic button, and this program will spit out a perfect database schema. That was the idea. Okay? And you see that kind of captured in the way that we talk about functional dependencies a lot. It's not really practical, though. And you'll probably get a sense of that on assignment 6. That assignment 6 has a lot of these kinds of examples where you have to go through, and it's basically learning a new kind of math. So How do you learn how to do long division? I don't know if you guys even do long division anymore. I don't like math changes so much over the years. But you practice a bunch of long division problems. How do you learn how to factor polynomials and junk? You factor a bunch of polynomials. The same thing with this. It's a new kind of reasoning, so you get to practice problems with it. But then toward the end, you'll start to see, oh, here's some problems, but really functional dependency analysis is really good at steering the human mind in good directions, but the human mind is still necessary to come up with the full schema. Okay? So intelligence is really important in this process. We can't really mechanize it fully. That was a big realization. That was kind of a bit of a disappointment, I should say. I think toward the end of the 70s and the early 80s when people were looking at this stuff. Okay, but I just wanted to mention that because that's kind of the historical context or the background of this stuff. And why, you'll notice, we go through so many of these examples with letters, and you might say, well, yeah, but how practical is this? Turns out it's practical, just not quite as practical as we all hoped. Okay, any questions about that? Because I know that's a bit of an aside, and it's actually more interesting than some of this other stuff. All right, cool. Let's see, axioms, rules of inference for dependencies. There's a set of 3 axioms that you can use, actually, to reason about functional dependencies, and you can prove things using them, and you can generate closures. You can generate closures of functional dependencies using these axioms. It's really great. So alpha, beta, gamma, and so forth. These are attribute sets. You have reflexivity. This is for trivial functional dependencies. Remember, these always hold. So alpha is a set of attributes. Beta is some subset of alpha. Then alpha functionally determines beta holds always. And so let's say that you have 5 attributes, A, B, C, D, E. Well, there's always a set of functional dependencies that holds on those attributes that are all trivial. Okay? They're not exciting, but they're there. Augmentation. So alpha functionally determines beta, and then you have another set of attributes, gamma. You can add gamma to both sides of the functional dependency. Now again, this is mildly exciting. I mean, I'm mildly excited by this, but kind of what we're saying here, because remember that functional dependencies are a generalization of keys? Remember how you can take any superkey and add attributes to it, and it's still a superkey? You get another superkey? Well, that's kind of the same idea here. You're adding attributes to both sides, no biggie, right? If alpha functionally determines beta, then alpha plus other junk also functionally determines that stuff. Okay, then you have transitivity. Alpha functionally determines beta, beta functionally determines gamma, then alpha functionally determines gamma as well. Okay, and this is the one we've already been kind of using as an example as possibly the most clear, the most reasonable one. Now, you will not be required to prove that these hold because it's irritating. And remember that I talked about, there's actually a book that's open source now, or I shouldn't say that, that's obviously that's for software and for other things, but it's in the public domain because it's old enough, and it talks about all this stuff, and it goes through how you prove these kinds of statements. So if you happen to be interested in it, let me know. I'll point you to the PDF, but it is not that exciting. The proofs look like what you would probably come up with anyway. I mean, it's not all that marvelous to behold. Okay, Armstrong's axiom. So we have the closure of F that we'd like, and we have F. So that's the functional dependencies that we know. We can actually compute the closure of F by repeatedly applying Armstrong's axioms. Okay? Now you'll notice that this is an iterative algorithm that will eventually reach a fixed point because we'll eventually reach a set of functional dependencies from which we can't infer any new ones. That's really kind of the point that is the fixed point. So each functional dependency F in the closure. So notice we start with the closure being just capital F. So that's all the initial dependencies that we start with. Apply reflexivity and augmentation. So what are we doing there? Well, we're adding stuff to one and or both sides. We add those functional dependencies to the closure of F. And then basically we look for things that we can use to generate new dependencies using transitivity. So alpha functionally determines beta, beta functionally determines gamma. Then I know that alpha functionally determines gamma as well. Add that into the closure of F. And if you keep doing this, then you'll end up with the entire closure of F. Okay? All right, so that's a bit of an assertion. And again, I'm not going to show you a proof of this because it's a bit beyond the scope of this course. But we do say that these axioms have certain characteristics, and again, they're proven in quite a bit of detail in this other book that I mentioned. That the axioms are sound. When we say that something's sound, we mean that it's not going to send us on to some weird false path in our arguments, right? So basically, we won't generate wrong functional dependencies. It turns out that they're complete as well, which is kind of interesting as an assertion. We will get the entire set of functional dependencies that can be inferred from F using these axioms. Remember, we're applying all three of them iteratively in a loop until the closure stops growing. Okay? It's possible, for example, to come up with sound axioms, but they're incomplete. Like there's still stuff you can't prove is inferable, or maybe you could prove it some other way, but your axioms don't generate it. So in this case, Armstrong's axioms are complete. And of course, the closure could be large. Now, this is the problem with a set of functional dependencies. If the closure is large, you don't want to write it all out. You'd like to be able to reason about it in some way that doesn't involve generating the entire closure all the time. Right? What a drag it would be to work with this all the time. Oh, and just to mention, of course, how many of these happen to be trivial dependencies? I don't know. I'm not good enough at math to be able to, you guys could probably do it after math 6 or whatever. But, so you've got a set of attributes, and then how many subsets can you generate from that? And if you look at all possible sets on the left-hand side, and then all possible subsets of those sets on the right-hand side, that's all your trivial dependencies. And those ones aren't even exciting, right? So that's in the closure of F as well. So you can, like I say here, it could be very large. There are other rules that are nice. They're helpful for being able to reason about functional dependencies. And so these are ones that you'll actually get to prove on assignment 6. And you'll note that they aren't that difficult to prove. So I don't think you'll have any real difficulty with this. So if alpha functionally determines beta and alpha functionally determines gamma, then you can infer that alpha functionally determines both together, beta gamma. Okay, so that's no biggie. Decomposition rule. Alpha functionally determines beta gamma, then alpha functionally determines beta, and alpha functionally determines gamma as well. Okay, so that's nice and easy. And then here's the fun one, and this is usually the one that we use on exam problems, and you'll see it appear. And this is about the subtlest of all the rules. Alpha functionally determines beta, gamma beta functionally determines delta, alpha gamma functionally determines delta as well. Okay, pseudo-transitivity. Okay. All right. The one thing that I want to mention is you'll notice that if you have two things on the right, so alpha functionally determines beta gamma, you can split them apart on the right. You're not really allowed to do the same thing on the left in general. So it's not a general thing that holds. If you have alpha beta functionally determines gamma, for example, that doesn't necessarily mean that alpha functionally determines gamma and beta functionally determines gamma. It may be the combination that's crucial there. Okay? So just keep that in mind. You don't want to get led astray. It's an interesting world in which you get to explore. Functional dependencies are a bit of a different way of thinking about things. Okay, let me ask. Any questions? Yes?
Just like from the algorithm on the previous slide, generate F plus in your like just database without any key constraints, is there any way to come up with the functional dependencies?
Well, so that's an interesting question. Could you come up with functional dependency constraints on your own without keys? Probably not, because remember like what I said in, I think it was 2 lectures ago, that just because you see values repeated doesn't necessarily mean that you have a problem. And so you'd have to have a very clever database that could, that somehow had enough information that it might be able to infer, hey, I always see these two values paired together, so maybe you could infer that kind of thing. I think the more interesting question is if you have your primary and foreign key constraints, because since key constraints are also functional dependencies, at least, so I guess I'm getting ahead of myself. Let me try to clarify my thoughts for you. I don't think the database could figure it out on its own just from the data, because I don't think just having the data is sufficient. You need a lot of data, and then you could guess. Your guesses may still be wrong. Okay, so that's the first part. The second part, so if you can't just guess them, then that means the database kind of needs to be told them. There's not a mechanism in SQL for stating functional dependencies explicitly. I think it would be really interesting to add a way to state functional dependencies and explore what kinds of new constraints you could enforce in a schema and whether that buys you anything, because I think that might be quite an interesting little project to explore. Okay, so you have to state them. There's already one mechanism that we have for stating functional dependencies, and that is primary key, unique key, and sometimes foreign key. So when you say something is a key, again, you can state that as a functional dependency, that those key attributes functionally determine everything in the table. So you know that at least. Once you know that, you can actually then figure out how functional dependencies come through relational algebra operations as well. For example, grouping and aggregation. The set of grouping attributes functionally determine all the attributes that are generated by the grouping and aggregation operation, which is a really interesting observation. Now, besides that, you may have functional dependencies about the input coming into the grouping and aggregation operation, knowing let's say that you have a grouping operation on A, B, and C. So that A, B, and C are the attributes you're grouping on. If you knew additionally that there was a functional dependency between A and B, like A functionally determines B, then you can infer additional things about the results of the grouping and aggregation operation. And the thing that's interesting about this is it may allow you to do additional optimizations that you wouldn't otherwise be able to do in your query planning. Okay? But I don't know that the win is big enough for anybody to put in the effort. And my only reason for guessing that is because nobody's done it. So, but anyway, that's kind of the long-winded explanation. Functional dependencies do make an appearance in a number of places in query planning and query evaluation, but nobody really takes advantage of it. And I think probably the biggest evidence that it's not quite worth it is that there's no mechanism for stating functional dependencies explicitly in the database. I still think that would be a really fun 123 project, but nobody's done that yet as a project. I hope that answers your question. Okay. Let's see. Yeah, you can imagine like the less data you had, the less certain you could be about the functional dependencies you think you observe in the data. That's the big challenge. And so a human being really has to be involved in that. Now, if you're talking Google levels of data or Facebook levels of data, you might be able to infer some things. So that's kind of an interesting thing. Okay, wait till you get to the next kind of dependency too. Then you'll be like, oh, okay, that would be even more difficult to discern just from the set of data. Okay, but I don't want to get ahead of myself. How to tell if an attribute set alpha is a superkey. Remember, we talked about this question before, and we said that if a set of attributes is a key on a relation schema, then another way of stating that, the more general way of stating that, is that the set of attributes functionally determines the entire schema. What we're saying is those attributes, the values of those attributes uniquely identify tuples within the relations. Okay, that's no problem. I can deal with that. So what attributes are functionally determined by an attribute set alpha? Because remember that there's a bit of a vacuum here. What attributes are functionally determined by an attribute set alpha? We need to know our set of functional dependencies. Part of that is our key constraints as well. Okay, so let's say we have an attribute set alpha, set of functional dependencies F. So we have this thing called the attribute set closure. Why is it called an attribute set closure? Well, because we're doing it on an attribute set. Alpha is an attribute set. So what we do is we write alpha plus, and alpha plus is alpha and all the attributes that are functionally determined by alpha. So you remember how I said A functionally determines B, B functionally determines C? If we had those two functional dependencies, like a really easy situation, then the attribute set closure of A would be ABC, because A determines B, B determines C, so you can infer that A determines C as well. So anyway, this attribute set closure turns out to be a super powerful technique for reasoning about functional dependencies without having to generate the whole closure of F. What a drag. Okay, and it's easy to generate. Let me show you how to do it. You start with the attribute set that you care about. You start with your set of functional dependencies, which, remember, like I said, includes key constraints. You start with your attribute set closure being your initial attribute set. Now you look at all your functional dependencies. If the left side of the functional dependencies attributes, if all those attributes on the left side appear in your current attribute set closure, add the right side of the functional dependencies to the attribute set closure. Voila, right? Just keep doing this. At some point, your attribute set closure stops changing, you reach a fixed point, you're done. Okay? All you're really doing is following all the functional dependencies out and adding in the things that are logically implied. I'm sorry, I didn't say that right. That are functionally determined by the left-hand side so far. So you just keep following out those paths until you reach the end. That's why when I said, if you had A functionally determines B and B functionally determines C, the attribute set closure of A would be ABC. Because A determines B, and then, so you add B to the set, and then B determines C, and you end up with ABC. Okay, so that means that we can use it to tell if an attribute set is a superkey. Notice we just figure out what attributes are functionally determined by that attribute set. And if that happens to include the entire relation schema, we're done. It's a superkey. Okay. So again, this is just sort of by definition, right, in a sense, because we're saying that keys are a special case of functional dependencies. Okay. Oh yeah, there's other ways of doing this too. So alpha functionally determines beta. So if we want to figure out if that functional dependency holds. So what we're saying is that alpha functionally determines beta is a proposed dependency. We're considering whether or not it holds. Then we can just look at the attribute set closure of alpha. So we're looking at all the attributes that alpha functionally determines. And if it includes beta, then we know that alpha functionally determines beta holds as well. Okay? Everybody got that? Because remember that by definition, alpha functionally determines alpha plus. And then you could actually use the decomposition rule to say, okay, well now I want to take the parts of alpha plus that aren't also in beta out, and then I can infer that dependency as well, if you wanted to be more formal about it. Okay? So find the closure of alpha under F, and if it contains beta, then you know that alpha functionally determines beta. Okay. Does that make sense? I hope this makes sense to you guys. Okay, so let's see, F plus. Attribute set closure as well. Yeah, so basically this is just an alternate mechanism for doing it. I couldn't tell you which one is faster. I know the one that I wrote before was I wrote a program in C++ to do the other mechanism that I described earlier in this slide, and it computed it really fast, so it's not like you need to be faster. But notice that here's an alternate algorithm. Basically, you go through every subset of R, including R, and you just go through and figure out what that set of attributes functionally determines. Okay, notice you find the attribute set closure of it, and then you can go ahead and break that attribute set closure down into all its subsets and generate another functional dependency for each one of those. Again, a lot of trivial dependencies in there that are not that exciting. I would say of the two approaches, this is definitely an easier way of doing it because it's just doing subsets. And I think everybody generally runs into how to generate all subsets of a set kind of problems at some point. I don't know if CS4 does that or CS2 will probably do that. It's kind of a ubiquitous problem. So this is an easy way of applying that to an attribute set closure to generate the closure of F. All right, let's see. Example. So here are a bunch of dependencies. Again, we have all our letters, which, what do they mean? I don't know. What do they model? I couldn't tell you. I wish I could. But that's just the nature of the beast. Is AG a superkey of R? Well, how do we solve this problem? Just like I said, if AG is a superkey of R, that means that if you have pairs of tuples, I'm sorry, let's just be more general about it. The values of A and G together uniquely identify tuples in R. That's what it means for it to be a superkey, right? Another way of stating it is that AG functionally determines R. So how do we figure that out? Well, we just compute the attribute set closure. So we start with, I think I have it on the slide. We can do it in our brains. This is easy, right? So AG, start with that as our attribute set closure. What do we add to it? Well, notice the first two dependencies. A functionally determines B, and it functionally determines C. So now it's ABCG. Okay. Hey, look, we have CG. Now we know that we can reach H and I. Right? So ABCGHI. That's everything, right? So it's a superkey. All right? Yay! That was, man, if all math were this easy. We'd all be, I'd be a mathematician then. I'm not a mathematician because I don't like math. Just turns out it's really useful. Okay, is AG a candidate key? What's a candidate key? It's a minimal superkey, right? So, fortunately, all proper subsets of AG is just A and G, so we can easily go through that. Is A superkey of R? How do you determine that? Just attribute set closure of A. Attribute set closure of A is A, B, C. Can we reach anything else? It's A, B, C, H. Because notice H is B functionally determines H is on the end. A, B, C, H. Can we reach anything else? No, because we don't have a G in there, right? Well, that's kind of a good indication that G is kind of important for being a candidate key. So we know that A is not a candidate key. G, what does G functionally determine? The wrong answer is nothing. Everything functionally determines itself. It's irritating, but it's a trivial dependency. So in this case, G functionally determines G. That's definitely not R. So is AG a candidate key? Yes, we can give that our stamp of approval. Right? So attribute set closures, so there you go. So AG is a candidate key. Any questions about this? It's the kind of thing you'll have to do on the assignments, and there's usually a problem on the final like this, like, here's some letters, and here's some functional dependencies. Tell me a candidate key and prove it. Ooh, right. All right. Boyce Cod. Let's go back to this. If R sub I is a schema not in B, C, and F, then there's at least, oh boy, yeah, I feel like stretching this out a little bit, except we're losing a lecture this week. I'll decide what to do later. Okay, so at least one non-trivial functional dependency. Alpha functionally determines beta, such that alpha is not a superkey for I. Yeah, first issue is that this is in the closure of F. Okay, we're not just looking at F. So it may be that there are dependencies implied by F that apply to a schema that are not explicitly stated in F. And you have to be careful about it. You have to pay attention to it. Also, for a particular schema that we're examining for Boyce-Codd normal forminess, or whatever you say, we really only care about the functional dependencies where the left-hand side and the right-hand side actually appear in that schema. That has a name. We call it the restriction. In fact, we call it the restriction of the closure to R. Okay? Because we really only care about those dependencies that hold on that particular schema. So how do we tell if Ri is not in B, C, and F? Well, there's a way of doing this with the attribute set closure as well, but it's a bit confusing to understand. So you go through all the subsets of attributes in R, okay, like I say here, and you compute the attribute set closure of each subset. Okay. All right, so that part's easy. Why am I doing that? Well, notice if the attribute set closure doesn't contain R, but it contains anything that's not on the left of that, let's say it's in alpha. Yeah, I don't want to get ahead of myself. So the attribute set closure doesn't contain R, but it does contain attributes in R minus A, so the initial set of attributes that you're starting with. Then you know that that schema is not in Boyce-Codd normal form. Okay, so that's a statement, and it's a rule. You can apply it, and it'll do stuff. But what I want you all to be thinking is, why is that true? Okay. What are we doing here? How do we know that this actually works? So if you compute the attribute set closure of alpha, so you have A plus now, and notice it doesn't contain R. What do we know about alpha with respect to R? Yeah. Yeah, we definitely know it's not a superkey. Okay, that's cool. Not a superkey of R. Attribute set closure contains attributes that are in R minus alpha. This is where it gets gross. Okay? Let me ask you this question first. If we had a dependency, alpha functionally determines beta, and I told you it's a trivial dependency, we know something about the relationship between beta and alpha, right? If alpha functionally determines beta, and I tell you the dependency is trivial, then beta is a subset of alpha, right? We know that those dependencies always hold, so we kind of have to get them out of the way. So if alpha plus contains attributes in R minus alpha, so notice I'm subtracting out alpha. By doing so, I'm saying, hey, yeah, I know there's functional dependencies that are trivial. Tell me the ones that are not trivial. So if there's some subset of attributes, R minus alpha, and those attributes still appear in the attribute set closure, then we know that this functional dependency is not trivial. So notice, it's like a backward way of doing it, but we've actually covered both parts of the BCNF definition. We've said alpha is not a superkey, and we've identified that there's some functional dependency that holds on R that's not trivial. So we have a problem. Okay, so beta is R minus, notice like I said again, alpha plus minus alpha. If this is purely trivial, then alpha plus minus alpha will just go away, right? Because you'll have the set minus itself. But we run into issues if there's other things functionally determined by alpha that are in R that are outside of alpha. Because those are the things that we actually are concerned about. So that means, and so you can see that we're just sort of stating it here more explicitly. Non-trivial functional dependency, alpha functionally determines beta. Okay, so we know that. This schema is not in BCNF. We can apply the decomposition rules. Okay, again, a little bit gross. This is a true rule. Again, I would suggest you study if you're not 100% convinced. But the cool thing about this is you can implement this. This is mechanical. You know, we had that other stuff before, like, oh, I've got to restrict F plus down to R and do all this junk and look at things and so forth. Well, attribute set closure is really easy to compute. So you can just take a schema, take every proper subset of that schema, generate the attribute set closure, do this test, and that'll tell you if R is not in Boyce-Codd normal form. So again, it would be easy to implement a program that does it for you, okay, if you are so inclined to do that kind of thing. All right, questions? All righty. Okay, so A, B, yeah, I want to make sure I get through the last topic here. So R, A, B, C, D, E, and F is A functionally determines B, BC functionally determines D. Is R and B, C, and F? Well, definitely not, right? Should be pretty obvious. We've got A and B in there together, and then other junk. Already that's an issue. So let's say that we use A functionally determines B to decompose R into two new schemas. One with just A and B, and remember that since A functionally determines B, I can make A the key if those two things are by themselves in the schema. So that's why I've underlined it. And then R2 is A, C, D, E. Now the question is, are we done? Because if you look at this and you look at F, you say, well, A functionally determines B, but A and B are not together in that schema. BC functionally determines D, but we're missing B. So maybe I'm done. Well, remember, like I said, that pseudo-transitivity is our favorite rule because it's a fun way of making things subtle. So it says that alpha functionally determines beta and gamma beta functionally determines delta. I can't even talk anymore. And it's not even Friday. I can't blame Friday this time. Then alpha gamma functionally determines delta. So we can use that rule to say, okay, A functionally determines B, BC functionally determines D, so I know that AC functionally determines D as well. And so that means, notice ACD, and then we also have E, so I need to go ahead and factor out the schema again. Okay? Yeah, another way of doing it again, if we were doing the rules that we just talked about on the previous slide, you could say, okay, let's look at all the proper subsets, and eventually you would come to the proper subset AC, and you compute attribute set closure, A, B, C, D. Okay, those are all the attributes that AC functionally determines. And then you look at R2 and you say, it also has E. So we have a problem here. I'm sorry, did I misstate that? I think I might have misstated that. So yeah, the reason why I misstated that is that AC doesn't functionally determine the entire schema. That was kind of the point of that. Okay? So AC doesn't functionally determine the entire schema R2, yet it also contains some additional attributes besides A and C. In this case, that are also in R2. And in this case, it's D. So AC functionally determines D. We can identify that this is not in Boyce Codd normal form. Okay, so we would have to decompose that into something like R2A and R2B, where it would be AC function, ACD together, and we can underline A and C because they're a key. And then we'd also have ACE with nothing underlined. Okay. All right. Any questions? All righty. Let's see what else we got. I'll see if I can get through this last part. This is actually really kind of important because it's third normal form. Constraints can become expensive. There's certain, and you may have noticed this. I hope you notice it as you do assignment 5. I looked and I thankfully included my notes in an appendix last year, so you'll see the appendix. What entity relationship modeling constraints are easy to enforce and which ones are hard to enforce? Good question. Participation constraints are really hard to enforce unless you can get everything into the same table and enforce them with a not null constraint. So not null constraints are easy, key constraints are easy. Anything that spans tables starts to get expensive to enforce in the database. And so we'd like to define our databases so that constraint enforcement is efficient. Okay? So if it involves multiple relation schemas, this is the reason why participation constraints are expensive, because they span multiple relation schemas and databases aren't good at doing those. Okay. Here's a bit of a concocted example, but it'll certainly illustrate the point. Each employee can work at only one branch. Okay, so we have a rule at our bank. You can only work at one particular branch. So we have this functional dependency. Employee ID functionally determines branch name. If the two appear together, a certain value of employee ID always has to have the same value of branch name. Okay. Then we say, I'd like banks to be able to assign a personal banker to every employee. Okay? Now, you could employee, every customer. So a customer could go to many different branches, and at each branch, they could have a personal banker at that branch, but they have multiple personal bankers over the entire bank, right? So we say we have this functional dependency. Customer ID and branch name together functionally determine employee ID. So you are my personal banker at this branch, and you are my personal banker at that branch, and so forth. Okay? The reason why you would have this kind of a scenario would be with an entity relationship diagram like this. Notice employees work in branches. A branch can have many employees. It should, because it's a bank branch. Each employee corresponds to one branch, so that's why we have an arrow on the other side of works in. And then we have a ternary relationship set between employee, branch, and customer. A combination of branch and customer maps to a single employee. Okay, everybody agree? Hopefully it makes sense. So these are the schemas we end up with. Notice we don't care about the entity set schemas. Those are easy to generate, but works in will have employee ID and branch name. The many side is the primary key, as usual. So employee ID is the primary key. Customer banker branch has branch name, customer ID, and employee ID in the schema, as well as the descriptive attribute type. And the many sides define the primary key, so branch name and customer ID together. All right? Okay. Let's see. So is this in Boyce Codd normal form? Well, this is where we have to look at our dependencies. Because remember that we had every employee has to work at one branch. Employees can't work at two branches. So we look at this and say, oh no, we have employee ID and branch name together in the second schema. And if you think about it, this makes total sense. I'm saying the combination of customer and branch should correspond to a single employee, but the presence of the employee ID kind of implies which branch I'm talking about, because each employee is already required to only work at one branch. Does everybody see that? So this is a bit of a drag. Not in Boyce Codd normal form. We unnecessarily repeat branch name. This is like sort of the problem with Boyce Codd. Boyce Codd is so strict about eliminating redundancy that when you have situations like this, where a little redundancy might actually make life a little nicer, Boyce Codd is like, nope, I don't want to waste any space. Okay? So we can decompose that. Now, of course, you apply the rules and you end up with employee ID branch name. We already have that. It's called works in. And then we end up with customer ID branch name and type. Do I have that right? Customer ID, employee ID type. Sorry. All right. So we've eliminated that redundant information, but now we have a new issue. I'll just show this to you because we're running out of time. We can't easily constrain that each customer has one personal banker at each branch. How would we impose that constraint anymore? We needed the branch name to be present so that we could enforce the constraint that the customer ID and branch name appears, each combination appears once. We can't do that anymore. Right? So this is an issue with Boyce Codd normal form. We say that Boyce Codd normal form is not dependency preserving. Now that's a general statement. Some schemas it will preserve all the dependencies. In certain circumstances it will not. Okay? So let me show you the punchline because I want to get there as quickly as we can. Third normal form relaxes one of the constraints of Boyce. It actually introduces another rule into Boyce Codd normal form that allows us to preserve more functional dependencies. But the cost is extra redundancy. Okay? So third normal form, you'll notice that the formulation is identical to Boyce Codd normal form with the addition of a new condition. Either alpha functionally determines beta is trivial, then we don't care. Or the left-hand side is a super key, then we don't care. And notice it's a super key for the entire schema that we're looking at. Or each attribute A in beta minus alpha. So we're talking about the right-hand side again. So each attribute A on the right-hand side is in some candidate key for R. That's a new additional constraint for third normal form. Now again, I'm going to have to skip over a lot of these kinds of details. I just want to point out that it's a general constraint. It's not a specific, like they all have to be in one candidate key. They could be spread out across multiple ones. I want to show you this. This was our non-voice code normal form schema. This is the one that's easy to enforce. Okay? And the question is it in third normal form? Well, we know that works-in is in third normal form. It's also in voice code normal form because we just have employee ID functionally determines branch name. Employee ID is the primary key. We're done with that one. We don't care. But then the question is customer banker branch. Because we know that there's a functional dependency. Employee ID functionally determines branch name, but employee ID is not the primary key of that whole schema. So the question is employee ID in some candidate key for that schema? And again, I'll give you the punchline because we're out of time. Yes. How do we know? Donnie's favorite rule of inference, pseudo-transitivity. Okay. We have employee ID functionally determines branch name, customer ID branch name functionally determine everything. Okay, because that's on customer banker branch. So let me just go ahead and throw this up here quickly. So so pseudo-transitivity, employee ID functionally determines branch name, customer ID branch name functionally determines the entire thing. So from that, we can infer that employee ID, customer ID, the combination, order doesn't matter in this case, functionally determines the entire schema. So we know that customer ID, employee ID, that combo also is a candidate key. Hooray! That's even better because now we've required that the combination of customer and branch must be distinct on that table. There's an implicit constraint that customer ID and employee ID, the combination, should also be distinct on that table. So we can go ahead and explicitly enforce that other dependency, and off we go. Okay, so this is in third normal form. Okay, any questions? I know this is very rushed at the end of this. Yeah.
How do we know that customer ID and employee ID is necessarily a minimum?
Well, that's a good question. How do we know that they're necessarily a minimum? Basically, what you would want to do is just sit down and figure out the attribute set closure of employee ID, figure out the attribute set closure of customer ID, see if they're an entire schema. I believe that they won't be. And so then that would prove that it's a candidate key. That's a good question, though. I haven't done that with this schema, so I can't tell you decisively. Okay, what I'm going to do is wrap this up now, because I know that was a lot of material, and we're over time anyway. But I'll see you Wednesday. We'll pick this up and continue talking about third normal form and how to reason about it.